You've probably seen that bell curve shape before, right? The normal distribution. Today on the deep dive, we're really going to unpack this core idea in statistics. We want to figure out why it's so fundamental and, where we actually see it.
Exactly. It pops up everywhere. Well, it's more than just that familiar shape. It's key for understanding patterns in data.
Okay, so let's start there. Why is it called the normal distribution? What makes it so central?
Well, partly it's because lots of things in the natural world just seem to cluster around an average value. Think about people's heights, for instance.
Right. Most people are around average height. Fewer are very tall or very short.
Precisely. But let's say the mathematical reason it's so central is really down to something called the central limit theorem. It's a really powerful concept we should definitely talk more about.
Okay, we'll circle back to that. When people see the curve, they often hear about the empirical rule. How does that connect with standard deviation?
Yeah, the empirical rule is a handy shortcut. It basically says for a normal distribution, about 68% of your data points will fall within one standard deviation of the average, or the mean.
68%, okay.
Then, about 95% fall within two standard deviations.
Right.
And almost all of it, over 99.7%, lies within three standard deviations.
So the standard deviation itself, it's a measure of spread.
Exactly. It tells you how tightly the data is clustered around that mean. A small standard deviation means everything's bunched up close. A large one means it's more spread out.
Got it. And what are the sort of key ingredients, the parameters that actually define one specific normal curve versus another?
Really, there are just two main ones.
Yeah.
The mean and the standard deviation. That's all you need.
And the mean is the center point.
Yep, it tells you where the peak of the curve is located on the number line.
And a standard deviation.
That controls the shape, how wide or narrow the bell is. Change the mean, the whole curve slides left or right. Change the standard deviation, it stretches or squishes.
Okay. Now, I've also heard of the standard normal distribution. What makes it standard? And how does it help figure out probabilities?
Right, the standard normal distribution is just a specific reference version. It's set to have a mean of exactly 0 and a standard deviation of exactly 1.
0 and 1. Why?
Its power is that we can convert any normal distribution, whatever its mean and standard deviation, into this standard form. Once we do that, we can use standard tables or software to easily find the probability of a value falling in a certain range. It standardizes the process.
That makes sense. But what if your data isn't perfectly bell-shaped? Which happens a lot in the real world, I imagine. Is that where transformations come in?
You got it. Real data is often messy. It might be skewed, meaning it leans to one side. Transformations are basically mathematical tweaks we apply to the data.
To make it look more normal.
Exactly. To make it better fit that bell shape, because a lot of common statistical methods actually assume the data is normally distributed.
Okay. And how do z-scores relate to all this?
Z-scores are super useful. A z-score tells you precisely how many standard deviations a single data point is away from the mean of its distribution.
How do you calculate that?
It's simple. You take the data point, subtract the mean of all data, and then divide the result by the standard deviation.
So a positive z-score means it's above average.
Right. And a negative one means it's below average. The number itself tells you how many standard deviations away. So a z-score of 2 is 2 standard deviations above the mean.
If data isn't normal, you mentioned skewness, there's also kurtosis, right? What are they telling us?
Yeah, they describe how a distribution deviates from normal. Skewness is about symmetry. Does it have a longer tail on the left or the right?
Okay.
Kurtosis is about the tailedness and the peak. Like, does it have heavier tails and a sharper peak than a normal distribution, or lighter tails and a flatter peak? These things matter because they can affect whether our statistical assumptions are valid.
We also use this normal shape idea for estimation, right? Like confidence intervals. How does that work?
Absolutely. The normal distribution is fundamental to constructing confidence intervals. Because we know its properties so well, like that 95% within 2 standard deviations thing, we can work backwards from our sample data.
To estimate where the true population value might be.
Precisely. We calculate a range around our sample statistics, say the average, and the normal distribution helps us determine how confident we can be, like 95% confident, that the true population average falls within that specific range. The standard deviation plays a big role in how wide that interval is.
It really does seem to pop up everywhere. Can you give a few more sort of everyday examples?
Sure. Besides things like height, you often see it as a decent approximation for scores on standardized tests, like IQ tests or SATs. Even things like measurement errors in scientific experiments often follow a normal pattern. maybe even sometimes short-term changes in stock prices, though that's a bit more debatable, especially for extreme events.
Right. So let's loop back to that central limit theorem you mentioned earlier. Why is that so important for making the normal distribution central?
Ah, the central limit theorem, or CLT. It's kind of magical. What it
Uh-huh.
says is, essentially, if you take lots of random samples from any population, doesn't matter what shape the original population's distribution is.
Any population, even skewed ones.
Yep, even really weirdly shaped ones.
Mm-hmm.
If you take samples, calculate the mean, the average of each sample, and then look at the distribution of those sample means.
Okay.
That distribution of sample means will tend to look like a normal distribution. And it gets closer and closer to normal the larger your samples are.
Wow. So the averages become normally distributed even if the original data wasn't.
Exactly, and that's incredibly powerful. It means we can use the properties of the normal distribution to make inferences about a population based on sample averages, even if we don't know what the original population looked like. It connects sample data to population inferences through the normal curve.
Okay, so wrapping up. The normal distribution is common because, one, lots of natural things cluster around an average, and two, crucially, this central limit theorem means sample averages tend towards normality anyway.
That's a great summary.
And we use the mean and standard deviation to describe it. The standard version helps with probabilities, and it's key for things like confidence intervals and statistical testing.
You've got it. It's a cornerstone of statistics for a reason.
So thinking about how often this pattern shows up, it makes you wonder, what does this tell us about underlying patterns in the world? And maybe more interestingly, where do you think the normal distribution doesn't really fit, even as an approximation? Something for you, our listeners, to think about.